Welcome to Lecture 7 of How to Read and Do Proofs. We have learned now the three quantifier techniques, the construction method, the choose method, and the specialization method. Let's take a moment to review them. When you see the keywords "there is" in the forward process, you know that there is an object with a certain property such that something happens. And you simply work forward from that object with all of its properties to create true statements. So there's nothing special to do in terms of a new proof technique. On the other hand, when you encounter those keywords in the backward process, then you have to show that there is an object with a certain property such that something happens. Anybody remember the proof technique for doing that?
Specialization?
No, that's for the quantifier for all. Eleanor, how about you?
The construction method?
Yes, the construction method. You have to go out and construct the object, produce it, devise an algorithm to create it, and then remember you have to show that the object you construct is in fact the correct one. It satisfies the certain property and the something that happens. How you construct this object is an art, but typically you'll turn to the forward process and use the information in the hypothesis to help you construct the object. You can also play with the properties that you want the object to satisfy to see if you can construct the right object. Okay, the other keywords that we learned are for all, for each, for any, for every. When you see those keywords in the backward process, you have to show that for every object with a certain property, something happens. We have a proof technique for doing that. Do either of you remember what that technique is?
Is it the choose method?
Yes, that would be the choose method. And how does that work? Well, what you have to do is choose one object with the certain property. That becomes information in the forward process, for which you have to show that the something happens. And that becomes your new statement in the backward process. And then you create this model proof in which you work forward from the assumption that X is an object with a certain property, and backward from trying to show that for that X, the something happens. And that becomes your model proof. Okay, and finally, we have the keywords for all arising in the forward process. In fact, when you see those keywords in the forward process, you know that for every object with a certain property, something happens. And in order to work forward from that information and create a new forward statement, now, Laurel, is the time for that specialization method. Okay, and the way specialization works is you try to identify one particular object with a certain property. Let's call it X. And then you can state that for that particular object X, with the certain property, it must satisfy the something that happens. And writing the something that happens as a new statement in the forward process, that's specialization. Okay, now all of the statements involving quantifiers that we have seen so far have contained one quantifier. Today what we're going to study is nested quantifiers. These are statements that contain more than one quantifier. Let's take a look at an example. Here in S1 you can see that we have two quantifiers. For every real number x between 0 and 1, there is a real number y between -1 and 1, such that x plus y squared equals 1. So here you see what we call nested quantifiers, two quantifiers, for all and there is. And now what I'd like to point out is the golden rule for working with nested quantifiers. And here's what it is. Always work with the quantifiers as they appear from left to right. In our example, the first quantifier you see in S1 is what?
For every real number?
For every, right? That's the quantifier. For every is the quantifier. So that's the first one that you see, and that's the one you want to deal with first. So for the quantifier for all in the statement S1, we need to identify the objects, the certain property, and the something that happens. So can you help me with this? What are the objects here?
A real number x.
Yes, a real number x. What's the certain property?
X is greater than 0 but less than 1.
That's right. And the something that happens?
There is a real number y.
There is a real number y with y between -1 and 1 such that x plus y squared equals 1. Okay. Now let's deal with this quantifier, there is. For the quantifier there is, let's identify the objects, the certain property, and the something that happens. What is the object here?
The real number y.
A real number y What's the certain property?
That y is between is greater than -1 and less than 1.
Y is between -1 and 1, and the something that happens, x plus y squared equals 1. Let's do another example. There is a real number m, strictly positive, such that for every element x in the set T, x is less than m. So here, the first quantifier that you see from the left is?
There is.
There is, exactly. And for that, we have to identify the objects, the certain property, and the something that happens. I'll do the objects, real numbers m, the certain property, m being?
Greater than 0.
Greater than 0. And what is the something that happens? For every element x in T, x is less than m. Now we deal with the second quantifier for all, right down here. So again, we have to identify the objects, which are what? Elements x and T. The certain property, there isn't one. And the something that happens, x is less than m. So in summary, all you have to do is work with the quantifiers as they appear from left to right. Now, the order in which the quantifiers appear is very critical to the meaning of the statement. So compare this statement S2 that you see up here. There is a real number m, strictly positive, such that for every element in the set T, x is less than m. Compare that statement to this one here. For every element x in T, there's a real number m, strictly positive, such that x is less than m. So what you can see here is that the quantifiers have been reversed. Here, there is comes first, and then for all, whereas down here, for all comes first, and then there is. This statement up here says there is one real number, m, strictly positive, such that all the elements of T are less than that m. There's one real number, m, and all the elements in T are less than m. But this statement down here is very different. This statement says that for every element in the set, there is a real number for which x is less than m. And that means that for one x, you can get a particular value of m for which this happens. But if you change the x, you might get a different value for m for which this happens. So these are very different statements, and hence the order in which you list the quantifiers is very important to the meaning of the statement. All right, let's do one more example here. For every real number epsilon greater than 0, there is a delta greater than 0 such that for all real numbers x and y with the absolute value of x less than delta, absolute value of f of x minus f of y is less than epsilon. So how many quantifiers do you see in this statement?
3.
3. For all, there is, and for all. And the key now is to deal with these quantifiers, or to process them, one at a time from left to right. So let's start with the first quantifier for all. What are the objects here? Real numbers epsilon. The certain property is being strictly positive. And the something that happens is everything else. Everything else. There is a real number delta greater than 0 such that for all real numbers x and y, with this property, this happens. Okay, now we can go down here and deal with the quantifier there is. What are the objects here? Real numbers delta. The certain property is being strictly positive, and the something that happens is everything else. And now we can deal with the third quantifier, for all. Identify the objects, the certain property, and the something that happens. The objects are what? Real numbers x and y. What's the certain property? Absolute value of x minus y less than delta. And the something that happens, absolute value of f of x minus f of y less than epsilon. Here's the golden rule for using proof techniques when you see statements with nested quantifiers. Again, process the quantifiers as they appear from left to right, and correspondingly use the construction, choose, or specialization methods depending on what you see. So we're going to apply proof techniques based on the order in which the quantifiers appear from left to right. So let's take an example here. Let's work with the definition of a function being onto. So here's what a function being onto means. For every real number y, there should be a real number x that you can put into the function and get out y. So for every real number y, there should be a real number x which you can put in the function and get out the value y. All right, let's use this definition to prove the following proposition. If m and b are real numbers with m not equal to 0, then the function f of x equals mx plus b is onto. So you've, of course, identified the hypothesis A and the conclusion B. What's the next thing you should be doing?
Looking for a proof method.
Choosing a proof technique, exactly. And to do that, you need to look for keywords, such as for all, there is, and we're going to learn some new ones today. So do you see any keywords in the hypothesis or the conclusion? No. Okay, so what technique should we use to get started?
The forward-backward method.
The forward-backward method, exactly. And so in this case, we're going to look at the conclusion B and ask a key question. Let's start the proof by asking the key question. How can I show that?
A function is onto.
Exactly. How can I show that a function is onto? To answer that question, that's when we're going to use the definition. So how do you show that a function is onto? According to the definition, you have to show that for every real number y, there is a real number x such that this function right here equals y. So that's what we're going to write as our new statement in the backward process. For every real number y, there is a real number x such that the value of the function is equal to y. We're going to process the statement B1 from left to right, and the first quantifier we see is for all. And so we need to identify the objects, the certain property, and the something that happens. The objects being what here?
For all real numbers y.
Real numbers y. Those are the objects. The certain property, there isn't one. And the something that happens is everything else. Now, recall that when you see the keywords for all in the backward process, you have to show that for every object with a certain property, something happens. We have a proof technique for doing that. Anybody remember what proof technique that is?
The choose method?
The choose method is correct. So let's choose an object with a certain property. And when you choose that object, in this case a real number y, that becomes information in the forward process. For that chosen object, you have to show that the something happens. So you have to show that for your chosen value of y, there is a real number x such that mx plus b equals y. That becomes your new statement in the backward process. Now we have to complete the model proof here. And in order to do that, you should look at B2 and recognize the keywords there is. And say to yourself, you have to show that there is an object with a certain property such that something happens. So what proof technique do you want to use now?
The construction method?
Now we have to use the construction method. And in particular, we have to construct a real number x for which mx plus b equals y. So let's solve this equation to find the value of x. We have to construct a real number x. Let's solve this equation for x. And here's how we do that, of course. You subtract b from both sides, and then what? Divide by m. In order to do this division, we need to know that m is not 0, because otherwise we would be dividing by 0. And this is where we use the hypothesis. So remember, I told you that when you use the construction method, you want to use the information in the hypothesis to help you construct the object. In this case, we're going to use the fact that m is not equal to 0 in the hypothesis so that we can divide by m here. So there's the construction of the real number x. But remember how the construction method works. According to the construction method, you have to show that the value of x that you constructed satisfies this equation here. And so let's take a look at how we can show that. Let's start with writing out what mx plus b is. Well, x is y minus b over m, and then the m's cancel and the b's cancel, and sure enough, you get y. All right, so now you've seen how to do a proof that contains nested quantifiers. Now what I'd like to do is have you practice reading a proof that uses nested quantifiers. So let's take a look at this example. If a, b, and c are real numbers with a strictly negative, then there is a real number y such that for every real number x, ax squared plus bx plus c is less than or equal to y. So here is a condensed proof of this proposition. Let's take a moment to read it. Okay, so our objective here is to try and understand these three sentences, S1, S2, and S3, in the context of proof techniques. Because as you'll notice, when you read the condensed proof, there is no mention of proof techniques. There's no mention of forward-backward method, construction method, choose, specialization. None of those methods are mentioned. I hope you've identified the hypothesis A, in which A, B, and C are real numbers with A strictly negative, and the conclusion B, there is a real number y such that for every real number x, ax squared plus bx plus c is less than or equal to y. Let's see if we can understand the statement, let y equal 4ac minus b squared over 4a. In order to understand this statement, you need to ask yourself, what proof technique is the author using? So if you're not sure, then ask yourself what proof technique you would use. Can you tell me what proof technique you would like to use to prove that this is true?
Because of the words there is, I would use the construction method.
That's right. Here you recognize the keywords there is and for every, but processing them from left to right, let's start with the keywords there is. And so you should think about the construction method. Indeed, that's exactly what the author has done in S1. The author has constructed the value of y, which we're going to now put as a forward statement in our proof. Construct y equal 4ac minus b squared over 4a. This is the construction method. According to the construction method, what does the author have to show about y? The author has to show that for that value of y, the something happens. And that something that happens is, for every real number x, ax squared plus bx plus c has to be less than or equal to y. So this becomes the new statement in the backward process that the author has to show. All right, so here's where we are. These are our forward statements, including the construction of y. This is our last statement in the backward process. This is what the author has to show. Let's take a look at what the author says next. For a real number x, you have that. This is true. Now we need to understand where that came from in terms of proof techniques. So for example, when you look at the statement B1, what proof technique would you use to show that for every real number x, ax squared plus bx plus c is less than or equal to y?
I would use the choose method.
This is correct. You have to show that for every object with a certain property, something happens, so you should think about the choose method. And how does the choose method work? You choose an object with a certain property. In this case, what does that mean you should choose? A real number x. And when you choose a real number x, that becomes information in the forward process, for which you have to show that the something happens. In this case, ax squared plus bx plus c less than or equal to y. This becomes your new statement in the backward process. If you look at S2, this is exactly what the author has done. When the author says, for a real number x, the author has chosen a real number x. And here, the author is starting to show that ax squared plus bx plus c is less than or equal to y. Ax squared plus bx plus c, the author claims, is equal to this expression here. In fact, the author leaves it to you to verify that this algebra is correct. All right, so here's where we are. Now we have to finish this proof, and the author does that by statement S3. Because a is less than 0, it follows that ax squared plus bx plus c is less than or equal to 4ac minus b squared over 4a, which is equal to y. Where does this statement come from?
Just a.
The hypothesis A, correct. The author needs to use algebra to go from A3 to B2. And so let's look at the algebra. From A3, we already know that ax squared plus bx plus c is equal to this big expression. That's already known from A3. Now, what do we know about A? It is?
Less than 0.
A is less than 0. And this number squared is always greater than or equal to 0. So negative times positive is?
Negative.
Negative. And negative plus something is always less than that something. So indeed, ax squared plus bx plus c is less than or equal to 4ac minus b squared over 4a. And that's exactly what the author has written right here in S3. And finally, 4ac minus b squared over 4a is y. That comes from a1. The proof is now complete because a4 is precisely the same as b2, the last statement in the backward process. Let's take a moment to summarize what we've learned in this lecture. Basically, what we have learned is how to deal with nested quantifiers, statements that contain more than one quantifier. And the golden rule is work with the quantifiers as they appear from left to right. So when you do that, you apply proof techniques, construction, choose, and specialization, according to the order in which the quantifiers appear from left to right. Any questions on nested quantifiers? That completes this lecture.